Hi, I'm Meta Spencer. Today we're going to be having the third session in the 35 week or 35 session series that Project Save the World is producing called Cool Thinking. And the series is named after the fact that the subject matter is the Arctic primarily. And we're looking at ways of cooling the Arctic or keeping it cooler than it seems to want to be going now. So there are a lot of technological proposals that have been made for how that can be done. And we want to look at them in depth. And one of the proposals has to do with the dispersal of iron salt aerosols into the atmosphere, not necessarily in the Arctic, because that might not be the best place to use iron salt, but we'll talk about that later. However, I have to introduce our speakers today with a little sad note, because all of us count as a dear friend by now, Professor Stephen Salter, who was one of the leading figures in the effort to find ways of cooling the planet from the crisis that we're getting into. And his work has been really extraordinary. He has done research that points the way to real solutions in something called marine cloud brightening. And he had a whole bunch of innovations throughout his career. But this past week, he passed away. He's been on this series of conversations a number of times before, and I've come to think of him as a dear friend. So we will certainly miss him. And I want to start the conversation off with Clive. I'll introduce you all in a minute, but one of our speakers will explain something new that has come out of their research, which bears upon the research that Professor Salter is leaving to us as his wonderful bequest to humankind. So our guests today are, if I look at them in my little thumbnails at the top from left to right, Peter Wadhams, who is a specialist in Arctic sea ice, knows more about the Arctic sea ice than I guess anybody else in the world, who knows? And he is in, I think, Turin, Italy. And Franz Oeste is an engineer who also has extraordinary expertise, and he is in Germany, and his thinking has led to some of the really important breakthroughs that we'll be talking about today. And I think in London, or at least in UK, is Clive Elsworth, who is a great participant in all of these activities. I think especially in the work with Franz on iron salt aerosol. And I'm going to ask Clive, if you will, to begin with a detour. In other words, we're not going to immediately be talking about the iron salt aerosol itself, but rather about how your recent research or Franz's research bears upon the work that Stephen Salter has been doing, and whether or not you had a chance. I want to know whether any of you had a chance to pass this good news on to him before he became too sick to understand. So, Clive, good morning.
Morning, Meta and everyone. Yes, so I work very closely with Franz. I have done for about 4 years now, and in the last, I don't know, 6 months, Franz has been getting more and more excited about clouds because of the chemistry that happens naturally in clouds, which is that I've got some slides we could look at later on this, how they help they're part of the natural process that removes methane from the atmosphere. And we wanted to point this out to Stephen, to say that this is very compatible with his idea of brightening clouds over the ocean to reflect more sunshine away and provide a cooling effect. You know, these things go hand in hand. And and so this was a delight to tell Stephen about this. It's become more clear as time has gone on, as you know, more researchers have produced papers. They make hydrogen peroxide, and Franz has looked more closely at this, and you know exactly how does this happen in this very small cloud droplets, and hydrogen peroxide splits in sunshine to make the radicals, OH radicals, that remove methane from the air.
Okay, now you were already over my head, and therefore, since I'm the mediator, I expect that there are people in the audience who also are going to need some help with what you just said.
Mhm.
Now, let's first break down what marine cloud brightening is, because it's a different approach from the iron salt aerosol applications that you two have been working on. And it's nice to see that there's a convergence, that the two approaches have some common outcome that we both sides would favor. That working with both iron salt applications and whatever you're doing with regard to clouds would be compatible with, and maybe even amplify the work or the findings that that Stephen's research was showing. So first of all, let's have somebody explain what marine cloud brightening is for the people who've never watched our shows before. Who wants to tackle that, or do you want me to do it?
Well, brighter clouds have more droplets and they're smaller. That's what makes something brighter. When you have so clouds are made of tiny, tiny, tiny droplets of water. It's dew that forms on aerosol particles. Rising parcel of air gets cold as it goes up, and as it gets cold, the dew forms on these on. There's always lots of little aerosol particles in the air, floating pieces of dust or something. And the more droplets you have, the brighter the cloud, the higher the surface area, the more sunshine gets reflected away. 23% of the sun's energy is already just reflected back out to space. It doesn't even reach the Earth's surface. And that's the amount of energy that comes into the Earth every day and leaves is enormous. So you only need to have a small percentage change in cloud brightness over the world to actually counter uh, the warming influence of the energy imbalance that we have today.
And Stephen was planning a technology that would involve spraying salt water into the air over oceans, which would float upward and brighten the clouds. Whatever clouds were there would become significantly or a tiny bit whiter than otherwise, which would reflect more of the light, which would cool the water below, and hence the world, right?
That's right. Absolutely right.
That's what he was doing. And he certainly has made a huge contribution, a leading contribution on that. Now, explain what iron salt aerosol research is, because you're doing different things. The goal is also to cool the world,
Can I put my slides up now?
whatever it takes.
Okay. We prepared these just in the last day, really. So let's give the background on methane removal, which is what iron salt aerosol is designed to do. It's designed to remove methane from the atmosphere, and Franz discovered that it's a natural process. It's marine, it's dust that blowing in we call it the marine boundary layer, in the layer of air just above the sea, above the oceans. And it makes special chemistry that removes methane. So let's just very quickly talk about methane, if I may, Meta.
Mm.
Methane is contributing around about 40% of the Earth's energy imbalance. So there's the difference between energy coming in and going out. It's measured in terms of watts per meter squared. If you think of a 100-watt bulb, you know, we don't really feel the heat of that anymore because we have LEDs, but it used to be when it was made heat, you could feel a lot of heat. And so it might seem like a small amount, but over the huge surface area of the Earth, 1.35 watts per meter squared, that is what is warming the Earth today. And that's a recent number from Jim Hansen in 2024. And methane has nearly tripled in its concentration from pre-industrial times to around about 2,000 parts per billion today. And it's producing, this is about 40%, 0.56 out of 1.35 watts per meter squared. And methane, we don't often see this figure, but every ton of methane in the air today, right now, is providing or exerting, you could say, 120 times the warming effect of carbon dioxide. Now, methane, as I've been saying, it gets removed from the atmosphere uh, all the time. And so that's what the next slide is going to talk about. But just before we talk about, you see a lot of people suggesting, well, we need to plug methane, we need to stop it coming out of gas leaks, would stop the cows from, burping and things like that. Somehow stop it from coming. There's a lot of methane comes out of coal mines. But then there's wetlands. There's millions of sources of methane. So it'd be very helpful if it can be reduced, if we can understand a bit more about how it gets removed from the atmosphere itself. So its average lifetime is normally thought to be round about 9 or 10 years. What we're saying is that can be reduced. So the problem with methane, I mean, it comes under the heading of what are called VOCs, volatile organic compounds. So there's all kinds of pollution that goes into the air from human activities and natural processes, but it mostly gets removed quite quickly because it reacts with these rather special little pieces, but they call them chemical species. This is part of natural chemistry in the air. That these little species, they're called oxidative chemical radicals. They really pack a punch on a very molecular level. But methane is rather inert. It's extremely inert. And so that's why it takes so long to go away from the atmosphere. But anyway, it does go away in the end from these. But once in a while, one of these radicals actually manages to react with methane to initiate its oxidation, as we say. Methane oxidizes. And so this is showing a couple of reactions here. Here's the OH radical. It was called the detergent of the atmosphere by Paul Crutzen, who won the Nobel Prize decades ago, actually, for this kind of work. But it's also known that just a single chlorine atom on its own is also really rather reactive, and it reacts with methane. This CH4 is methane here, 16 times faster than the OH radical. And so this is very interesting for us that it works 16 times as fast. If this can be harnessed somehow safely to remove methane from the atmosphere 16 times faster than the main method, the OH radical, oxygen hydrogen, that is, then we could be onto something. So this is what we're excited about. Recent papers have been describing large-scale creation of hydrogen peroxide. So this is 2 hydrogens and 2 oxygens. We've all heard of that. People use it in their hair. And it splits in sunshine to produce OH radicals. You might think, well, so what's the big deal? You're still talking about OH radicals. Well, here's the interesting chemistry. In the atmosphere, let me just go back to the previous slide. The reaction product, when chlorine removes methane, you get this HCl here, HCl, hydrogen chloride, and HCl can recycle the chlorine. So we're very interested in anything that recycles the same thing round and round and round and round, so that we don't have to put huge amounts of, I mean, you can't, it wouldn't be allowed, and it would be a very bad idea to put huge amounts of chlorine into the atmosphere. But if you can have a very small amount of chlorine in HCl that gets used again and again, see, because the OH radical reacts with HCl to produce our chlorine atom that removes methane 16 times as fast. So this is the sort of level that we work on all the time, Franz and myself. We talk about all these things, every time we meet. So it means that HCl, the content, is catalyzing very fast methane oxidation. And if people are worried about, HCl, that's when it mixes with water, it makes hydrochloric acid. That's what's in our stomach to make our stomachs naturally acid. We need that to digest our food. It's also made in the marine boundary layer by reaction with airborne acids with sea salt, aerosol. This is part of the reason Franz suggested long ago that iron-salt aerosol, which is iron chloride, where does this iron chloride come from? Well, it comes from the kind of rust, iron oxide in mineral dust, and the acids that come from marine life, quite naturally occurring phytoplankton produces that. So this, I won't go into this too much, but there's a incredibly high voltage. This is 10 million volts per centimeter. Of course, this is a very large expanded picture of a cloud droplet with very cloud droplets are very naturally acidic on the outside. They're quite if you know about acids, it's disturbingly acidic. This is naturally how it occurs, like pH 0 on the outside.
Clouds in general are acidic.
Yeah. The droplets is acidic on the outside, and that's the opposite of acidic on the inside. So you could say alkaline. Chemists say the word basic. So you have this very, very sharp difference right within the cloud droplet itself: acid on the outside and very alkaline on the inside. And okay, so then you get this
stuff. Excuse me, but you're showing here a droplet.
Yeah.
And this is a map of a droplet, and you have this OH in the center, and and on the outside, I don't get it. You've got H3O, or you've got various combinations. Now, all of those things.
It is made from water itself.
Those are all acid, right?
Right. So the H3O is acid. So this is, water. We all know water to be H2O. But when you look down on a molecular level, you find that it's doing all kinds of, interesting things. You get an extra hydrogen, which is why we have this H. We've got an additional plus here. So that's an extra kind of proton, if you like. It's a hydrogen ion, the OH without its water. So this is not an OH radical. This is a hydroxide ion. So I told Franz we cannot give a full chemistry lesson in 15 minutes, but this is vitally important to this whole subject.
Let me try to imagine what OH is. In my life, where would I have seen some OH, and what would it look like or smell like?
Every kind of base, like sodium hydroxide, is a base. If you dissolve it in water, it has sodium plus ions and OH minus ions. These OH minus is a characteristic of a base. It makes an alkaline pH. And the opposite, an acid, is always, if you, for instance, if you have nitric acid or sulfuric acid, or so, these are always, they have always an H3O plus. This H3O plus is normally the proton. Water is H2O, and if you have one H more, then you get the plus.
Now, if I were I'm trying to imagine, do anything that I have in my kitchen or bathroom that might look like what you're describing here. What would this H3O look like if I had a whole handful of it?
If you in your bathroom, the water H2O, in a very small amount, it is split also in these OH minus and H3 plus, and this is measured by a pH. If you have a pH of 7, that's neutral, you have the same amount of H3 plus and OH minus.
Do not run into any of this stuff separately.
Well, vinegar is an acid. Vinegar is an acid. Citric acids. So, lemon juice, that's acidic as well.
I see. So that would be a lot of H3O in that, in the vinegar or
you could say there'd be a lot of H3O in that. Yeah.
It depends on the pH.
But that would be an acid. Like, what would that be about?
Acid in our stomach is about pH 1. It's rather acidic. You can say.
you know.
Okay, so now here I've got an idea. Here's a droplet of water in the clouds. And what's going to happen to it now? What good thing is going to happen?
What's going to happen is it moves around in the cloud, and as it gets to the top of the cloud, it actually starts to evaporate in the sun. And
Mhm.
so the droplet gets smaller and smaller. And it's been making hydrogen peroxide with there's a whole thing we're not showing here, but there's extra slides for anyone that
With the oxygen
chemists that want
from
this.
outside.
Yeah, the oxygen comes in from the outside. It goes and we can sort of see one, and then it's getting a bit closer, and it gets into here, and it reacts with the OHs to make hydrogen peroxide. So as the thing droplet evaporates, it just leaves behind hydrogen peroxide. So eventually, when the droplet is completely gone, it's just water vapor has just disappeared into the air. It's just evaporated into the air. You're just left with hydrogen peroxide as a gas in the air. So that's the good thing about it. It leaves behind this hydrogen peroxide, which then the sunshine splits the H2O2 into two uncharged OH radicals, which are very reactive, and they remove methane.
Okay, now this is the big event that we're celebrating is when this thing evaporates. And now tell me again how you have eliminated methane by this process.
Yeah. So this produces hydrogen peroxide, and what we would call oxidative radicals get produced from hydrogen peroxide. So hydrogen peroxide is H2O2. It splits in sunshine to produce two OH radicals. And if I go back to my previous slide, so OH radicals, these are known as the detergent of the atmosphere by atmospheric chemists. All atmospheric chemists, they learn early on in their lectures at university that OH is the detergent of the atmosphere. It removes the things like methane. So methane is one of the very hardest gases to remove from the atmosphere. There are many other things, just gasoline, all the things that make up gasoline, and alcohols. You can smell alcohol, and many, many other things that come as a result of pollution get removed from the air by OH. This is constantly cleaning up the air, but it takes a long time to get rid of methane. But as I said, what we're interested in very much is the fact that a single chlorine atom on its own removes methane at least 16 times faster than the famous detergent of the atmosphere. Chlorine is a rather more effective detergent. We have to be rather careful with it. But the point is that when chlorine removes methane, this CH3, by the way, that disappears on its own quite easily. It's very reactive. It reacts with the atmosphere to become water and carbon dioxide, which is much less of a greenhouse gas.
Sorry, CH3 is methane.
Well, no, CH4 is methane. One carbon and four hydrogen atoms bonded to it. And then CH3, we just call that, what do we call that, Franz?
Methyl radical.
Methyl
radical.
Is
the first stage of methane oxidation.
Yeah.
This makes the methane oxidation very easy for oxygen and other things which are oxidative in the atmosphere. And this is done by the OH or Cl radicals, first stage.
And so what the iron salt aerosol, why people are interested in that is that also makes chlorine radicals. It emits a single chlorine atom on its own. Chlorine usually likes to be charged, so this is part of chemistry, but it occurs it gets emitted without any charge on it, and that's very reactive, and so it also reacts with methane. And so once this has happened, once the methane, which really plays hard to get, once you've hit it with one of these and produced a CH3, you don't have to worry about it anymore, because that disappears very quickly. That's gone within a few seconds. So what took years, 9 or 10 years or more, before we managed to get rid of it, methane, in the atmosphere with one of these radicals. As soon as this has happened, this CH3, we kind of almost forget about this because we know it disappears again very quickly. So what we're interested in is the fact that it's made an HCl. The chlorine has, what's happened to our chlorine? The chlorine is combined with one of the hydrogens in methane to make HCl. And that's very useful to us because it's then still around in HCl, that if we have an abundance of OH radicals, which we're seeing that clouds produce an abundance of OH radicals in their droplets as they evaporate. These abundance of OH radicals then release the chlorine atom again as a chlorine radical. So once it's made available again, it can then remove another methane molecule, and then they can go around in this cycle.
So you need only one chlorine atom to oxidize thousands of.
That's right, thousands of methane molecules. Yeah.
Well, now, if that's the case, how come it hasn't become a runaway endless thing? Why do we still have any OH in the atmosphere? Because if you just had a handful of it'd be like a fission process where you start the thing and it would multiply, wouldn't it?
You have HCl in the atmosphere over the oceans. Over the oceans, you have about up to 800 ppts. That is a very low number of HCl. And so if we think with 10 times more than these very tiny number of 800 ppt, we can work much better in the clouds to reduce methane.
And in the end, it runs out of methane. In a cloud, once the methane is gone, then the reaction can't keep going around anymore.
Okay, all right, hot diggity. All right, so this is this a new discovery or something? And by the way, whatever happened to the iron salt? We have stopped talking about iron
because you don't have to put any solid particles in the air. Now, we're not saying there's no role for iron. Iron is very good also because the ocean needs iron for life. There's most of the ocean doesn't have enough iron for the growth. This is what iron fertilization is all about. So we really think that dispersing iron very, very diffusely as an aerosol would be a great way to just increase the life in the ocean.
Like nature does.
But apparently that's not essential to what you're describing here.
It's not. There's a couple of slides here because I knew you wanted to talk about clouds as well and brightening clouds. This is part of the whole thing. And this is a quote from Alan Gadian saying that the power of brightening clouds. He actually said, I asked him, could I quote you on this, Alan? He said yes, if I say this. So I've quoted him verbatim here. We know that from the warming unleashed from reduction of sulfate emissions from shipping exhaust, so this new regulation, they're not allowed to put so much sulfur, a lot less sulfur going in the air. The cooling influence of low-level stratus clouds can be enhanced to reduce solar radiation arriving at the surface. And this could cool the Earth's surface, and in extreme could potentially be enough to induce another ice age. So when he said that in a meeting in October last year, I asked him if I could quote him on that, because this is extremely important for people to know the cooling power of marine cloud brightening.
Hold on now, let me make sure I got it, because I don't think I have. We know it's sulfur coming out of the ships that causes these trails, right? These things you can see from satellites. It's the sulfur in the bunker fuel, right?
That's right, yeah.
Okay, now, so when they stopped the bunker fuel use, then there's less clouds to reflect light back out of the atmosphere. Suddenly the Earth got significantly hotter. If you put a lot more, then if you not only reverted to using bunker fuel, but let's say just used a whole lot more bunker fuel, it depends on how much you use, but if you used enough, you could create an ice age by cooling the planet enormously. That's what the implication is that he's saying?
Yeah, it doesn't have to be sulfur. There's many other ways of making clouds brighter. But that's what's been happening for the last many years with sulfur and fuel.
Okay,
But yeah,
now
that's right. That's what he's saying. Yeah.
here's the question to me. It took me a while to realize that what you're talking about isn't just iron in the atmosphere, but there are a number of other aerosols that could also have this some similar chemical effect that would turn the methane into CO2 and water. And how many aerosols are there that would do that? I mean, if it's sulfur, well, I'm not sure that we want a whole lot more sulfur in our atmosphere. If it's salt water, I think that's probably less ominous. Salt water you can handle because you got the oceans. But how many other things? I think I heard Franz talk about titanium a few months ago. So there must be a lot of other little particles that, if they're in the atmosphere, would have the same effect of brightening the clouds and reflecting radiation or sunshine back
Right.
into space, right?
There are some photosensitive compounds that we're interested in. So iron is very photosensitive. It was used in one of the earliest photography technologies, iron actually, and titanium is also photosensitive. Also, nitrate is very photosensitive. So nitric acid has been seen to make a big difference to producing OH radicals. It's photosensitive in a way that makes these oxidative radicals that oxidize methane. So it's anything that makes these oxidative radicals. They're the key to it. Is the OH radical and it's chlorine radical mainly. And these photosensitive compounds, titanium oxide and hydroxides of iron and nitrate, these are the main ones that make these oxidative radicals. But we love this idea, we love this discovery, recent discovery, that cloud droplets make hydrogen peroxide, because we know it splits to make OH. Also, it splits to make OH radicals, and OH radicals can turbocharge. You only need a tiny little bit of chlorine, and they will use this chlorine to remove methane very quickly. So cloud droplets that make hydrogen peroxide that's split by the sun, and also iron. So here's the thing I was moving towards. We've got some extra slides here. We always put some extra slides for these extra questions. So here's hydrogen. It goes on forever, I'm afraid. Meta chemistry of the atmosphere is wonderfully complex and interesting. So here's hydrogen peroxide once again, H2O2. And some researchers, Franz told me this, they talk about iron dust in clouds producing bursts of OH radicals. And this is not a recent discovery. This is called Fenton reactions, which they will operate during the night as well. If you have a little bit of iron dust, it's sort of mineral dust that's got a little bit of iron in it. Nearly all mineral dust has got some iron in it. So a lot of iron in the Earth's surface. It has this reaction that converts hydrogen peroxide into bursts of OH radicals. And so here we've listed all the same reactions here. Once again, we see OH with methane becoming water, and this CH3 that disappears very quickly. There it is with HCl. So there it is displacing the chlorine atom, which that can then be used, and which then removes methane very quickly. So this is the one that happens 16 times faster than reaction 4. Actually, here we've just mentioned here the CH3 plus atmospheric oxidants. That eventually, the methane eventually just goes away to become carbon dioxide and water. And we'd rather it wouldn't become carbon dioxide, but that's the kind of that's the end product for most oxidation reactions involving carbon. It's still a greenhouse gas, but it's nothing like as powerful as methane. I mean, methane is 120 times for the methane that's there right now, before it starts getting removed.
And all these reactions happen in nature now. And since eons of years.
Billions
For
of years.
instance, think to the sulfur compounds which come off the phytoplankton in the sea. Before the industrial area, where we had much more phytoplankton in the sea, we had also more sulfur in the air, which has been
we had more what in
replaced
the air? I'm sorry, Franz. Say it again. I'm slow. What? Say it again.
I thought you told from bunker fuel it has much sulfur, and I said this sulfur emissions had come in and are coming from the phytoplankton. This
sulfur.
is
Sulfur is coming from it.
Yes, and as dimethyl sulfide, if you are going on the shore of the ocean, you smell it, the smell of the sea, that is dimethyl sulfide.
Bimethyl
sulfur
sulfide.
compound. And this is oxidized in the air and ends as sulfuric acid, the same sulfuric acid which comes from the bunker fuel when it goes as SO2 in the air and oxidizes there. The same. This is in principle the same process.
But in the olden days, it came from phytoplankton in the ocean.
Also, but in the olden days, we have now much ocean places which are more blue than green. And the more green you see, the more phytoplankton is there, and the more dimethyl sulfide is produced.
So why are we having less phytoplankton today?
That comes from the fast warming. The fast warming
is killing the phytoplankton.
Indirectly. It makes the ocean surface stratified. So you cannot have, if you have a very warm water at the surface and a cold water more deep, then the different layers stratify, and the exchange between the two layers from below in the ocean is enough iron and all things which phytoplankton likes. But nutrition, if you have these stratified ocean surface, it goes short in nutrition. And so, Clive, you can explain this better.
Well,
because
you've done it quite well. Yeah. I mean, this is a big problem with the warming ocean. This is very rapidly warming the ocean, compared to geological, speed of things. It's very, which means you have this density-induced. Peter would explain this as well. Peter's ocean physicist. Your density-induced stratification. So warm water at the top. Normally, when so parts of the ocean where, especially you find it in the in the polar regions, the temperature gradient is not so different as it is in the tropics naturally. So you get much more mixing. The ocean is full of nutrients all the way down to the bottom, full of iron, nitrates and phosphates and silicates. These are the main nutrients. Lots of micronutrients as well, but these are the main ones. And phytoplankton, all life needs these. Marine life needs, especially, iron is usually the main one that's missing. But if you have, as in this is the reason why the tropics tend to be the visibility. If you go diving, you can see for a long way because there's nothing much growing there's not much phytoplankton growing. And so, but there's a general move of the whole of the ocean to, this on a geological timescale, very rapid warming, which is stratifying the ocean, which is reducing the mixing of nutrients, and so levels of phytoplankton. It's different in different parts of the ocean. Of course, the oceans are absolutely vast. It's difficult to measure. Actually, recently there's a recent launch of the PACE satellite, which is going to measure phytoplankton, the colors, it's what the P stands for phytoplankton in PACE, actually, phytoplankton. Aerosol and climate, something else. They're going to be able to determine much better how much phytoplankton is growing where in what parts of the ocean. You get phytoplankton blooms happen quite naturally. You get these undersea volcanoes. I mean, nobody knows when an undersea volcano is going to go off, and it produces a wonderful nutrition in that part of the ocean for phytoplankton to grow.
Oh yeah, okay.
And always where you see the green phytoplankton, you see also the clouds. You can see it very impressive from the satellite photo. Clive has this wonderful photo.
Yeah. So this is another physical process that we learned from Stephen, that this thing about the dew forming on a part of the air called where it's become supersaturated with water, where the air cannot hold that much water vapor anymore. So the water's trying to come out and condense onto something, and it condenses onto droplets. But the tiniest droplets, there's this kind of tug of war going on. It's this was called the Kohler. Stephen described it as the Kohler curve, Kohler, where there's this kind of tug of war going on between the surface tension of this tiny droplet and what's called the vapor pressure of water trying to condense onto the droplet. So the tiniest droplets have a real hard job getting going, actually getting to grow. But the slightly bigger droplets, you know, the vapor pressure on the surface area of the droplet is enough to overcome the surface tension. So these are called accumulation mode droplets. It's a sort of cohort of droplets. You know, the accumulation mode, they're that much bigger that they can easily grow. And the little tiny ones, you know, the air has to be very supersaturated, very cold, and desperate to get rid of its water vapor for them to actually grow. Now the thing is that if the water, if the the air contains, or the droplet is based around something we call it hygroscopic, something that's attracting water, like sulfuric acid, you know, the H2SO4 molecule, or sulfuric acid, or salt, or a salt particle. Salt, we know that salt, if you leave it out, it kind of attracts water, doesn't it? You have to sort of keep it in something dry. And sugar's another thing that attracts water. And so that's why having more sulfuric acid in the air, it makes these droplets grow more easily, to become accumulation mode droplets, to become the millions and billions and trillions of droplets you see in clouds. So having a little bit of acid, natural acids from phytoplankton, dimethyl sulfide is naturally emitted from phytoplankton. Again, it's not a terribly straightforward relationship. It seems often when they die, they produce DMS, dimethyl sulfide, which oxidizes to make sulfur dioxide, which oxidizes further to make sulfuric acid. And this makes the cloud droplets more hygroscopic. They absorb water more easily. They grow more easily. So you get the tiniest particles. We call it nucleating a cloud droplet. If you don't have a little bit less natural acid in the atmosphere, you actually get a lot of particles in clouds that haven't made a droplet. So you've got fewer droplets. The water had to be shared out among more cloud droplets, which are all bigger. So what did I say? Did I say that right? You've got some smaller number of larger droplets, a smaller surface area. The cloud looks darker. It doesn't reflect as much sunshine. It doesn't do as much cooling. This is what we learnt from Stephen.
Now let me, we only have about 10 minutes left, and I'm trying to absorb what you've said, and I'm also trying to see what are the implications of it. By the way, while you've been talking, Clive, we've been joined by Adele Buckley, my friend here in Toronto, who's a physicist and engineer, and she's a Pugwashite, so she was very much engaged in the last series of conversations that we had about this topic. So welcome, Adele. Everybody will have a chance to ask a question in a minute, but let me try to focus this by asking, what are the action implications of this? I thought I knew what we were supposed to do with iron salt. We were going to go out there and spray it around. and that's going to knock all of the stuff out of the atmosphere, I can understand that a little bit. But now I'm not quite sure what our next game plan is in terms of actual technology of what we're going to do to take methane out of the atmosphere. It sounds like you've got some good news, but how come it's good news, and what are we supposed to do as a result?
We can work with simple salts as to feed the methane depletion by clouds.
Yeah.
We don't need this complicated mechanisms we had before.
It's very easy to make salt nanoparticles, very tiny particles. Okay. So Stephen and many others are proposing very specialized nozzles to make these tiny, tiny droplets, less than a micron size, or I think it's a bit more than it evaporates, become a bit less. But you can make salt particles simply by mixing certain gases. You can mix HCl with ammonia gas, and it reacts to make ammonium chloride salt particle. Very, very tiny particles. These are hygroscopic. They nucleate cloud droplets. So we're offering. I mean, we're not saying, oh no, you've got to stop. Stephen's ideas, I think people are pushing that forward, and they like that idea. It's got a lot of momentum behind it. So I wouldn't want to suggest that should stop at all. No, they should keep going with that. We're offering another option on the table here and saying that you can make salt particles very easily, very cheaply. You could
with that. In other words, we don't have to wait for that nozzle. Because his problem, the problem I think with the marine cloud lightning is the bottleneck is they haven't got the right nozzle yet that produces the right size particles. Now, are you saying that you don't need a nozzle anyway? There are other ways of doing it?
We need no nozzle. No,
you don't need a nozzle.
It's much easier.
Well, what is the good?
You can see this. You have a bottle with salt,
like salt
acid. The
ammonium chloride,
HCl.
Right.
A bottle with HCl solution and a bottle with ammonia solution, and hold them with their open them and hold them
next together.
Then you see a white
mist
in the air,
and that's ammonium chloride salt particles.
That's ammonium chloride, a very tiny, extreme tiny particles of ammonium chloride. That's a simple salt and not toxic.
Are you saying? Sorry, but let's go back to this nozzle thing. How are you going to make life easier for everybody? Are you saying we don't have to wait for this nozzle to be perfected? That there are other ways of dispersing what would do the job in the atmosphere?
Yeah, that is what we're saying. Yes, I mean, we're not saying we've got something that we can just deliver tomorrow. But somebody needs to pay for something to be made. I mean, we're saying that you can find videos where chemists demonstrate this. They put the two next together, or they'll just have some air bubbling out of these two things, and you see the mist getting made. It's ammonium chloride. So it's quite low tech, and it wouldn't take much at all. It'd take quite a small amount of money to put together a system to make that and test it in a marine cloud brightening experiment.
Now, were you able to tell Stephen about your discovery, and did this make him happy before he passed on?
We did tell him, didn't we, Franz? We gave him those reactions.
Yes.
So and he offered us the use of his spray tunnel, which he sent us the design for, which hasn't happened yet. He didn't get the funding for it. A spray tunnel for us to test these aerosols in, and we said, look, actually, I told him, I said, we feel a bit embarrassed here because this is a competing idea to his spraying of salt, and he said, don't worry about that. If it works, that's important. That's what's important. So he was supporting us in getting it tested. but the funding wasn't there, and it still isn't there yet.
Well, in time it will. I'm going to be quiet because I've hogged the time completely. I'm going to ask Peter and Adele to I'm sure you have questions or comments.
Well, I guess I don't have a lot of questions. I don't mind all the slides with the reactions. Those are fine with me. But what would be a source of funding? And would it have to have any international approval in order to do an experiment? And it seems to me that more information is needed, and we need a project with money behind it in order to go further.
Mm.
Are you asking me and Franz?
Well, anybody, how do we get funding to do this? I mean, what body can be applied to for funding?
Somebody has to apply for funding. We now get more offers of funding than we have time to apply for. We're so busy developing these ideas and writing up papers on them that we haven't got around to applying for funding recently. So
maybe you don't want funding yet. Maybe we'd rather not for a little while.
I think we do want funding because I have to support myself by doing other work. So it'd be nice to be able to work on this full time. Yeah. So it's just there's so much to do now. Franz, this is not the only ideas we've had. There's so many. Franz is an idea factory, basically. He comes up with ideas all the time. And keeping up with him is about as much as I can do. And we do have other people. You name it. Plastic in the ocean, so many things. We could come and talk about that another time, perhaps. A bigger team of people to collaborate with us to manage, funding applications, manage the whole process. We have actually joined with a company that's that they're based on producing iron-salt aerosols called Blue Dot Change, Californian company. They're working with shipping companies to distribute iron-salt aerosol. But and we've told them we've got better ideas now, and we want them to hear about all these ideas as well. But these companies, they have to have a plan. They if they get their own funding, and they have to explain how they're going to make money. And so people like me and Franz who continually come up and saying, look, there's a better idea. They just sort of kind of say, well, look, we'll have to put that in the pipeline. That we can't just keep changing things all the time every time you have a new idea. But we would like to have research funding. They're the only ones so far that have put money on the kind of table. They've actually produced, bought their own equipment. They've got their own chemical engineer. They've been testing iron-salt aerosol. They've seen it removing methane repeatedly. It's interesting. They took it out in the car park, this rig, and it worked better because it was real sunshine coming in
outside.
Outside in the car park, outside the building.
Much better than artificial light.
Yeah. So we've applied over the years for funding. I don't know how many times, but they're the ones that actually put their own money on the table and said, this will happen. So.
But where did you apply for funding?
I can't remember now. I think it might have been the Hewlett Foundation. Was it, Franz? Hewlett.
Various American foundations or European.
Well, I spoke to ARIA. This is a British group, Advanced Research something, and they were very interested for a while. I think they still are interested, but they've kind of gone a bit quiet for the last couple of months. I haven't heard anything. Occasionally I'd chase them up and I say, yeah, hang on in there with there's another announcement. I think everybody's very busy.
But what you're discovering is neither one of them, the new ones don't cancel out the value of what you've done before. It's just that you're on a roll and you're producing more and more new ideas, and they're all wonderful. Is that it?
That's it. That's pretty much it. Yeah, that's right.
Yeah. Peter Wadhams, you have been silent this whole time, and I'm sure you have comments or thoughts about this.
Well, the comments I guess, similar to what Clive has said, that in fact, I was trying to do a bit of homework before this meeting, and encountered this absolutely astonishing collection of ideas that Franz and Clive had, which were, and you'll see if you see hundreds of slides in which suddenly there's something which you can do, which is related to this question of iron salt aerosols, but allows you to do something that you didn't think you could do. And the equivalent, I suppose, with Stephen was he was thinking about a way of moderating hurricanes,
Yes.
which was completely seemingly unconnected with marine cloud brightening, but it turned out that it ought to work for moderating hurricanes. I mean, no, probably, and I hope it doesn't have to die with him, but somebody should be picking up on that idea and seeing if that is really valuable enough to have an impact on hurricane frequency. So I think some of the ideas that relate to the chemistry of the atmosphere that we've been hearing today, you look at the background and there's a whole load more. So it's
now these are I don't have the impression that what Franz is proposing is just crazy speculation. It's clear, right? I mean, it's scientifically factual. Is that right? That this is what is going on in the atmosphere, and we're just now discovering how it works. It's not that you're guessing how it might work sometime if we, if we approach it well, or maybe it works this way. You're saying this is how it works, facts.
This is all
right?
good stuff. It's good. It's good science, and so the great sort of gold mine or iron mine of material here, which actually is something just on the side. Clive mentioned the possibilities of what you can get out of a mine, and in fact, there's a project at the moment. I'm going to look at it shortly, because there's in the wet, that there's processes that go on in the wet bottoms of coal mines. That's flooded coal mines that have just got gunk, liquid gunk floating around in the bottom. And it turns out that the chemistry of the bottoms of wet coal mines include the creation of very valuable materials, rare earth elements, for instance. And somebody should be sucking all that water out of the coal mines and processing it, which I think America is starting to do. But the hope is that we can do it in England or Britain. And there's a disused coal mine up for grabs in Scotland, which people are interested in for that purpose. So,
well, there you go. Here's another topic for a whole new forum, or maybe a whole series of forums. Who knows? Sucking water out of the bottom of coal mines. Yes, a new topic for me. Okay, we've used our time up, friends, and then some. But it's been not only a challenge to me to follow this, because I think I got a C in high school chemistry, and I haven't improved on my record since then. So it was a challenge, but I got the general drift of it. I think I understand the argument, and I'm delighted to have the impression that it's not just speculation, but it's solid, proven reality. So that means we have something more to work with, and that's progress. It's science, the way things are supposed to work in science. Thank you all. You're all saving the world, and that's just terrific. Thank you so much.
Thank you,
too, Meta.
Meta.
Thank
Thank you,
you.
Meta.
Bye-bye.